In this video, we'll discuss a common approach to solving larger problems and see how it applies to our racquetball simulation. Larger problems are much more challenging to solve than smaller problems. Our brains are not very good at remembering all the details at once that are necessary for the entire problem. The standard technique is to break a problem down into subproblems. It is much easier to solve a number of smaller problems than trying to solve one big problem all at once. While solving each small problem, we do not need to think about the details of the other problems. Another key concept that is useful to apply is known as abstraction. That is the process of understanding important concepts while ignoring unnecessary details. An analogy is that in order to drive a car, we can ignore the details of how the engine and transmission work. We just need to worry about how the steering wheel, gear shift, accelerator, and brake pedal work. By abstracting away the details that we don't need to know, we've made it easier to concentrate on the issue at hand of driving the car. Here is one possible first attempt at breaking the racquetball simulation down into smaller subproblems. First, we'll print an introduction telling the user what it does. Next, we'll get the inputs. We can then simulate the games and finally print the results. While working on each of these steps, we won't need to worry about the other problems. It is common to write a function for each subproblem. Because the code for each function is independent of the other functions, we can focus on solving just that subproblem. Here is a pictorial representation of the functions corresponding to the 4 steps we discussed on the previous slide. The other thing this diagram shows is the data we need to communicate between functions. The incoming arrows into the functions along the bottom row are the data the function needs, so those will be parameters. The outgoing arrows from each function along the bottom row are the results it is sending back to the main function, so those will be return values. As you look at this diagram, one of these functions still seems fairly complex, so we could consider breaking it up into a subproblem to do some of the work. Here is our second attempt at designing the code. Because the sim_endgames function seems complex, we decided to break it into a helper function that simulates one game. After simulating a game, we can use the accumulator pattern to update the totals of how many games each player won in the sim_endgames function. Here's the final design we will use. We decided to write a helper function that determines if a game is over that we will call from the sim_one_game function. Note the arrows show the data that is being sent as parameters and return values. One of the primary reasons for writing functions is to avoid repeating code. In this design, we will not be calling the functions from multiple places, so that is not the reason for using functions for this program. The other reason for using functions is to make your code more organized and to break it up into smaller problems, each of which is simpler to solve than the original problem. That is the reason we are using functions in this program. Let's review the steps to follow after breaking a problem down into subproblems. First, we make a function for each subproblem. The interface or signature of a function is the name of the function, the parameters, and the return value. As we saw with the pictorial representations, we can draw arrows to indicate the data that needs to be sent back and forth between the functions. This will help you write the signature with the parameters and determine what the return values need to be. This process of breaking it down into subproblems is commonly referred to as top-down design. Now you can work on each function separately. One common approach is to start by implementing the functions at the bottom of the diagram, since these functions do not call any other functions and can be tested before writing the functions at the next level up. This is appropriately known as bottom-up implementation. Another approach that is sometimes used is to write simplified versions of functions that follow the signature by taking the appropriate parameters and returning values, but do not do the full work they are supposed to. This is an example of a concept known as prototyping, in which you build a version that doesn't meet all the requirements before building the final version. While building the prototype, you may learn something that will help you determine a better way to build the final version. In the next video, we'll use a mixture of these two techniques as we write the code for the racquetball simulation.